Since there has been some confusion around the coordinate system conventions used by flow5, I thought it would be a good idea to make a short explanation. There are three coordinate systems that are worth keeping in mind. The first coordinate system is used for geometry input. Its x-axis is pointing backwards, y-axis along the right wing, and z-axis upwards. It is also used as the reference for the angle of attack and the side slip. Note that you may still rotate components in the plane editor. You need to consider this additional rotation when interpreting the results later on. If you rotate the wing by 5 degrees, the actual angle of attack of the wing will be 5 degrees greater than the analysis input. The second coordinate system is used for the output of all coefficients, forces and moments except stability derivatives. It is aligned with the aircraft's velocity relative to the atmosphere and also referred to as the wind coordinate system. Similar to the geometry coordinate system, its x-axis also points backwards, its y-axis towards the right and z-axis upwards. The third coordinate system is called stability coordinate system and exclusively used for the output of stability and control derivatives. It is only rotated by the angle of attack while the side slip is ignored. Contrary to the other coordinate systems, its x-axis points forwards and z-axis downwards. Now looking at some example analysis, we can verify that the outputs are what we expect. I have used the default plane to prepare two configurations, ones unchanged and ones with deflected ailerons. Note that the right aileron is deflected upwards and the left aileron downwards, which should roll the airplane to the right. For the default plane, the lift coefficient is positive and increases with an increase in angle of attack. Similarly, the drag coefficient is positive and increases with an increase in angle of attack. As described earlier, the wind coordinate system's x-axis points backwards and z-axis upwards, so the results are as expected. Looking at a side slip analysis, we can see that the yawing moment coefficient, Cn, becomes negative with positive side slip angles. Looking at the plane view makes this a bit more intuitive. Let's turn on streamlines. As we can see, positive side slip angles correspond to the nose of the airplane pointing to the left, with the oncoming air hitting the plane's right side. Therefore, the lift produced by the vertical stabilizer points to the left. Since the z-axis is pointing upwards, this produces a negative yawing moment around it by right-hand rule. Looking at the analysis with deflected ailerons, we can see that the rolling moment coefficient Cl is negative. Since the x-axis is pointing backwards and the ailerons are deflected to produce a right roll, this is again as we expect. Now looking at stability derivatives, we can verify that the axis directions are as described earlier. The Cz alpha derivative is negative and the Cn beta derivative is positive. An increase in angle of attack leads to an increase in lift, or in other words, an upwards directed force. An increase in side slip, that is the nose of the aircraft pointing left, leads to a restoring moment, trying to yaw the aircraft to the right. Since the z-axis points downwards in the stability coordinate system, this is as expected. The same applies to CLP. Since the x-axis points forward, a positive roll, that is rolling the aircraft to the right, increases the angle of attack on the right wing half and decreases it on the left. Consequently, the right side produces more lift and the generated moment is therefore negative. Finally, note that the steady state coefficients produced by the stability analysis are given in the wind coordinate system, unlike the stability derivatives.